Hello? Yeah, that's quite cute picture by Minjourney. And welcome to my talk today. I'm quite excited to be here sharing about my fuzzing techniques on Apple ecosystem. Yeah, let me introduce myself first. My name is Zhenpeng, and I'm now working as a security researcher at Star Labs and focusing on Apple and web bug hunting and exploit. And previously, I shared some of my research at ZeroCon and POC. And today's agenda will be simple, but I prepared like 75 pages about it. I hope we can finish it in 30 minutes. Yeah, so basically that you could learn about some background knowledge about the Apple ecosystem, the structures like Mac, BSD, IOKit, and part of the coprocessor. And I would also review the bug in each subsystem later in the bug analyze part. And also the attack services in the Apple ecosystem and mitigations, as well as my vulnerability research thoughts. So that looks like kind of the keynote part. And then you will learn how to develop a simple but effective fuzzer from scratch. Is really simple, and the golden ticket towards some easy Apple zero-day series, probably. Yeah, so let's start. So XNU is Apple's kernel. It's a hybrid kernel, consists of three parts, like the Mac, BSD, IOKit, and the Apple devices got several coprocessor to always-on processor, the display control processor, the smart I/O, security clay processor work together with the application processor to so the Mac represents the micro parts in XNU, and the most represented object I think is the Mac ports. It's a general wrapper for kernel objects and message queen, which is the Mac IPC. It can carry the raw data, the writes, like the send receive equals to the read and write writes, if you're familiar with the Linux, and it also can carry the memory. So other objects in Mac will be like the Mac task, thread, and voucher. So the BSD is the monolithic kernel part of XNU. It implements the traditional Unix structures like the file descriptor, the socket, and device drivers. And IOKit, I would say that it's the most shitty part in XNU because, like, if you're trying to understand in the wide exploit of Apple, you would say like 70% of them will exist in the IOKit part. So it's a subset of C++ written driver framework and implements some tool drivers like IO service, frame buffer for like GPU and family series. And network filter and endpoint security is actually part of IOKit, and they're already moved out of the kernel scope, now served as the system extension in user space. And there's also other drivers that communicated with the peripherals, like the coprocessors, like the Apple M2 Scala CSC driver. And for coprocessors, I also categorize them like those who, from the I/O registry entry, is the device tree, like the object that maintained by kernel dynamically, and we can see that I/O service instance like Apple M2 Scala CSC driver and Apple AV2 driver and connected directly to the coprocessor instance. And there's also others that communicate with the mailbox. If you see that the com.apple, the driver, the Apple A7 IOP is the implementation of the mailbox mechanism on Apple system. And in this one, you got a simple endpoint for PMP that is corresponding AP side driver. It's called Apple PMP v2. And there's also other coprocessors that had a rich functionality and features that can provide a lot of services For example, like the secure Eclipse processor, that the Touch ID, the Face ID on iPhone was based on this coprocessor. And why not also talk about that part this morning? So we can see that there was a driver instance called the Apple SAP Manager, managed multiple endpoints from the AP side to coprocessor side. And for example, like the Apple SAP key store is corresponding user space driver in SAP side is called the SKS. And there's also other like type is act as a tool. It's not used directly like the Smart I/O. That maybe you can also find there's a user client called Apple Smart I/O user client in the I/O register entry, but it's never initialized because the PEI can have debugger function. And this is usually used by other drivers, for example, like the DCP-related drivers. Based on that, I draw a simple picture to review the relationships between the user space, the kernel, and firmwares. And let's come to the attack services part, because I said that was 3 different that subsystem in X and U, so it also got like 3 different APIs, syscalls entry point or so. But IOKit APIs, what is under it is actually called Mac message, which is one of the Mac traps. And yeah, an MIG system is also based on that, but that's another story. You just remember this 3. So for coprocessors, we got some remote attack services, for example, like Wi-Fi and baseband and Bluetooth. For like local attacks, for example, like DCP, the SAP, and GPU. And so my bug mainly exists on the like DMA and memory mapped I/O part, that mailbox which is based on the memory mapped I/O. So if we do the compare between these 2 parts, compare the mitigations, we will find that in X1U we got strong and significant mitigations, and I believe that this morning, why not already talk about that? I would say that some software mitigations like the SAP Feng Shui, the VA Squeezer, and variant of KL type, some hardware mitigations, and Apple is still keep isolating the user-controlled memory, for example, like the K-memory range ID spread quarantine. So for this part, if you're interested, I strongly recommend you to read the last year's HackerCon, the Life and Death as an iOS hacker. And if it comes to the coprocessor part, you will find almost no modern software mitigations in it, like no ASLR, no heap mitigations, although it's got some like hardware mitigation like ACIP is a coprocessor side KDR and PPL, and to prevent we attack from the coprocessor to the AP side, Apple introduced a thing called IO Dart, is Apple SMU. But usually if you can gain code execution at the coprocessor side, it won't be hard to trigger other bugs on the AP side. So when I would start the work, I was wondering that if a coprocessor is so tasty, why didn't everyone just target on it? So it got really limited public resources, like, and it needs like heavy reverse engineering work, and it's hard to debug or determine the runtime memory layout for the exploit part. But personal opinion, I think the coprocessor could be really valuable targets in the future under the modern mitigations in X and U. The limited public resources can mean more possibilities, and yeah, the reverse engineering work is tough, but we can finish it by time. Yeah, we can also emulate the firmwares to solve the debug problems. And then we begin our fuzzing part. So I will first do a quick review of the version 1 and and like compare the improvements in version 2. Like in the early fuzz stage, I would collect the entitlements needed by the driver, sign the fuzzer, and collected all reachable like I/O services and the user clients, because like for one I/O services, it will got my different type of user clients. And then I would like start the early fuzz stage to collect effective data and generate the playlist and provide it to the deep fuzz stage. There might be some other trivial operations like rank potential vulnerable cacks. So the difference mainly exists in the two yellow line parts. So for the entitlements collection now, I use a IDA Python script for it. I would collect all code near call X reference to the entitlement getters. For example, here it will be like IO user client copy client entitlements, but there are also other getters such as like IO task has entitlement or some in IO GPU. And we can see that it uses ADRL instructions to load the entitlement string address to X1 register, which is the second parameter. And then we find the data offset extracts from the ADRL instructions to get the string address. But usually it's not all the case, but because we can see that the entitlement string address might not just load by the ADR instruction. It might load by the upper function. So here we will need to handle some special cases of it. And then we need to get the entitlement string from the xreference.2 with the UTF-8 encoding. And then I collect 177 entitlements based on the iOS 16.3 kernel cache. And for the user client collection part, that previously I was using the method that mentioned by Brandon Azar, use the iOS service iterator. But then when I was auditing, I found that some part was missing by that kind of method. And I found that there was a key interesting in the IO regis entry called the IOKit diagnostics, and it's a dictionary. So the classes key in this dictionary will contain all the IO service and user clients on the system. Even some of them are not present due to the hardware issue. So I just like retrieve the master port and get the root entry and then get the properties of it. And yeah, I get the classes dictionary and do the same as I do like the version 1 stage. Yeah, that's it. And but this kind of method do has a limit that only can be used in the non-sandbox environment on iOS, for example, like the jailbroken device and SRD. But interestingly, that it can work on the macOS sandbox app. So I don't know why it's some configuration or what. Or you can just run it in a non-sandbox environment like a terminal. And after the improvements applied into the fuzzer, you can find that it improved almost twice the attack services than before. And if it comes to the deep fuzz stage, this time I would do the input data mutation and risk memory, risk condition and share memory fuzz, and the info leak detect, and some driver independent backhand by code audit, mainly to use the code audit effort to bypass some state machine check in the IOKit. So here I would mainly talk about the backward fuzzing based components introduced in version 2. So you may be wondering, what is backward fuzzing mean? That usually we use code audit to find bugs that the forward process will be like, we do the code audit and then we find bug and we construct a proof of concept to verify it. And here I just found some public proof of concept or some binary diff the bugs I found and extract the pattern and then use it to reproduce small bugs by fuzzer. And the basic idea will be like what happened in the past will happen in the future. What happens here will happen there. So it looks like from 2 dimensions, from the time and space, I will reuse or migrate the pattern to produce more bugs. So here it looks like a bit of high level, so let's understand it by some real cases. So I got 3 sources of the components. One is from the code diff and binary diff. Okay, so here's a 20-year-old tag service by Codif, and it's quite simple that you can see that it only removed the address format print from the IO log, and this would like put the address of the kernel pointer into the syslog, and yeah, it's quite simple and quite easy to fix. And this bug actually introduced in IO audio family in 2002, and it's fixed in 2016, but we're now at 2023, right? So does the story end here? Or could be more? The root cause will be like the kernel developer might write the kernel address to a log by accident. I think this could be a general attack surface, not only in IOKit, but in XNU or coprocessors. So let's examine it. And due to the unified logging mechanism, if you are using like grep or some static analyze method to just find the address format print, you will find that some are not true because it will just show private. So you must like to find it dynamically. So you need a way to trigger a lot of code paths in your target. So the fuzzer can do that. And another effective way to detect the kernel inflake, and we can done that by the search the syslog and add a grep filter. So the bug just bump out your eyes, and I will pick some of it in different fields and to show you that, yeah, I just yellow line them and you'll be quite straight. And it's in our Bluetooth family. And this one is in the DCP image that, yeah, it's the same pattern, but in the firmware's image. And if you want to reverse it and check, I strongly recommend the blog post by Yambirs, the 0-day in the white exploit in the DCP. I always use his way to reverse engineering and analyze other bugs in DCP. So here the bug is also simple. Yeah, another simple bug. Yeah, it's silently patched before I report it because I need to take some time to write all the reports. It's a lot. And how about XNU? That in kernel, that the things seems a little bit different because like the address format printed only used in some cases, like it's used in the panic context, so there's no window, and or it's commented, or it's not enabled for release version. So yeah, more than 20 bugs have found by this, and Apple will merge some issue within the cache. So 5 was assigned, and another one I think is assigned like yesterday or the day before yesterday in iOS 16.5, and there's more on the way. If you're interested in this area and want to get some CV, you can just go ahead. And also, I get some inspirations from the public proof of concept that, for example, like this one, like I learned that limited resource management will be like a huge problem in kernel. Like I learned a proof of concept from the MPTCP integer overflow by Pangu team. So we're gonna use this idea to migrate it to other parts. And let's see if we can find some other similar issues. And here, I do find some issues by this idea in different parts in IOKit, Mac, BSD, and coprocessor. And the coprocessor part is partially fixed now. So yeah, I will release more informations later and give you a hint. So in IRKit part, the bug is stupid. Like normally, CACs will inherit the IO user client and re-implement it, inherit the IO service and re-implemented the new user client method, and sometimes they just return 0, which means the return success. But due to the like memory limit in kernel space, the client won't be like properly initialized. So, yeah, when it's used later, it will trigger the non-pointer somewhere. And because I report like more than 10 issues for this problem, and Apple addressed like a general fix for it, and so it will try to dynamic cast it to a user client. If not, it will return error, then dereference it. But there still exists some watchdog timeout issue even within the sandbox, like the Apple upstream user client driver for Intel device. And for Mac ports, we can got the integer overflow for IPC port, that there was a macro called the IO max references, and the value was changed from the 0x7 followed with 7f to 0x0 followed with 7f since iOS 15. So here we can send 0x2000 SAM port to the 0x8000 different remote port. Why we do that is in order to bypass some check in the XNU IPC. And yeah, in this way we can trigger it and we'll get a panic within the sandbox. And on latest versions that I already reported, and after, I don't know if they fix it or not because it was converted to the memory exhaustion on the latest version. It's not the latest version because I didn't have tested on iOS 16.5. And yeah, so is the issue also exists for BSD drivers. Like the proof of concept was even tweetable, and yeah, you just keep opening the perform monitor and you'll crash. And if the DMNA was used as an index to the perform monitor devices, yeah, it's stupid. And on the latest version, it also converted it to the what the mutex is unexpectedly owned by thread. And I didn't dive into the detail of it, but if you're interested, you can check it. I don't know. So there would also be some like mind-blown ideas through code audit. When I was doing code audit, I might like think up some pattern that could exist in real cases. Like this one, if the abstract pattern would be like a function A calls function B and returns the return value of function B. But function B actually does not have a return value, it's a void type. Usually this problem won't exist for pure C function if you're not using the directly function pointer, but it could exist for the virtual method for C++. So in this case, it was in the IO report hub, and it would like, due to the calling convention, it would return the RX register to the user space, and the RX register in the IO service clause will be like stored a meta class pointer in it. So when it's just returned to user space, the higher 32-bit will be straight, but the lower 32-bit will be enough for you to like bypass the kernel slide. And there's some other tells about the coprocessor bugs that this was actually found in the early stage, but usually I would consider bugs found by the early stage as non-exploitable because I haven't do anything about the data mutation yet. It just crashed and it got different panic contexts, like there would be a active panic or a non-pointer. Actually, the RDLS will only reveal the register value when you trigger a data abort other than the active panic on it. And yeah, it's not interesting. If you like read about my previous slide and you implement yourself, you can find it. And it's in Apple CLCD too. And for the diff fuzz stage, I like this one is like partially fixed. I trigger a data board on it, and I can change the FAR by user input. Like the FAR register is much more interesting than previous one because if it's a non-pointer, the fault address register will be 0, and yeah. But what I can tell is in the general one, not a specific designed backend fuzzer. And yeah, like coprocessor bugs will be hard to understand from AP side because sometimes, like when I find a panic and I try to understand from AP side, it will like it just write a user control value to a memory mapped IO region, and it crashed. Like it write to like a normal region, seems no harmful at AP side, but it will trigger other things for the coprocessor side. Or it takes like a memory descriptor, like it allocs IO slave memory and start DMA. And here's a like brief description of other bugs found by the version 2 that which is also all by the like general part of it. And for the SIO part, I found both bugs in the driver and its firmware. And this bug actually is not used directly, but used by the DCP-related driver. And here's the summary part. I would like to give some of my experience and hints about it. So variance bug hunting, like by fuzzing, it could be easy if you get the idea behind the bug, like what is its real root cause, and is it easy to like make the mistake by the developer in other subsystem. And some bugs like could be easy to find by fuzzer and hard to find by code audit because you can't quite understand it by that context. You need to combine other things together. And so code audit and fuzzing are not opposite. We can combine together as a hybrid way. They're mutually reinforcing. And for the reference part, I want to like thanks for John's talk at last year's HacksCon, like the motels from the iOS macOS kernel trenches, and from his example that inspires me to get a new pattern that find more bugs. And yeah, I recommend you to read that. And also thanks for Ben Azar for the initial version of my fuzzer, the IO service iterate part. And yeah, the Lucas slide about the life and death as an iOS attacker. Yeah, here we comes to the end, and thanks for you guys coming to my talk and OffensiveCon for hosting such a wonderful event. Thank you all.